Hello everyone. We present curve height estimation using 2DLiDAR mounted on e-bike. To publish open data such as pedestrian network is important to realize barrier-free environment. The pedestrian network includes some barrier data, for example, slopes, curves, and so on. From this kind of background, we are trying to collect barrier data using sensors mounted on e-bike. In this paper, we focus on detecting curves using 2DLiDAR. Before I introduce how to detect curves from sensor, I'd like to explain about 2DLiDAR. 2DLiDAR is the distance measurement sensor, also known as 2D laser scanner or 2D laser range sensor. The picture to the right is the top view of the 2DLiDAR and shows scanning mechanism. 2DLiDAR measures the distance to an object by illuminating the target with laser. The difference between 2DLiDAR and 3DLiDAR is the number of scanning lines. This means, in other words, 2DLiDAR senses using only a single horizontal scanning line. In many cases, 2DLiDAR is used for performing detection and ranging tasks. From this part, I'd like to introduce how to detect curves and estimate their heights. The method contains three parts. The first is coordinate transformation. The second is curve detection and height estimation. And finally, curve identification. To obtain variable information from distance measurement sensor, first of all, we should define the coordinate for our application. Getting raw data from 2DLiDAR, we convert them from polar coordinates to Cartesian coordinates as we defined by this equation, where R and psi denotes distance and angle values of I sample in one scan, phi and theta denotes roll and pitch angles of 2DLiDAR respectively, and R represents rotation matrix and H denotes the heights of 2DLiDAR. Note that the rotation matrix R can be measured by IMU sensor. In the next slide, I'll explain how to detect the curve and estimate its height. In this step, we attempt to get start and end sample of the curve from each scan by the differential of z-coordinate values. This process contains 5 steps. At first, we calculate the differential of z-coordinate by using this equation, where n denotes the total number of samples in one scan. Secondly, we determine threshold value to judge whether I sample represents a curve or not. To determine threshold value adaptively, we use sample identifier method because the scanning data may be noisy when bicycle moves. Next, we extract set of samples where the absolute differential value exceeds the threshold. The extracted sets of samples represent curve regions. And then from the extracted set of samples, we acquire the samples corresponding to the minimum and maximum values for y-coordinate. These minimum and maximum samples represent the start and end sample of the curve. Finally, we can get the estimated curve height by taking the difference between the z-coordinate values of the sample corresponding to the start and end samples. As the final step, we obtain curve data in time series applying density-based clustering algorithm to detected curve data. The reason why we apply density-based clustering algorithm is that the position of the curve does not change rapidly in time series. So we assume that the start and end samples of the curve in each scan does not change largely even if the bicycle moves. In this experiment, we chose DB scan algorithm. In the next slide, I'd like to show you our experiments and experimental results. We conducted 2 experiments to evaluate the estimation accuracies of heights and positions. As an experimental equipment, we built a prototype system using 2DLiDAR and e-bike and IMU as shown in the picture. In the next slide, I will explain about our experiments. First experiment, we evaluate the estimation accuracies of heights. As shown in these pictures, we collect the actual curve data, which heights are 150, 90, and 50 millimeters. And we collect them in 3 different moving attitudes: stationary, walking, and running. We evaluate our proposed method applying these actual data. Here is the accuracy result of estimated height. The result shows that more than 50 millimeters height curves can be detected with high accuracy. The estimated heights of curves are less than actual values because the inside samples are detected. Next experiment, we evaluate the estimation accuracies of positions. As shown in these pictures, we collect actual curve data, which positions are minus 600 and 850 millimeters. Note that the negative sign follows the coordinate system that we defined before. Here is the accuracy result of estimated positions. The result shows that the curve position can be estimated with high accuracy than that of curve heights. I'd like to conclude by making the following points. To obtain curve information from 2DLiDAR, we proposed curve detection method, which contains these 3 steps. To evaluate accuracies, we built a prototype system by using e-bike and 2DLiDAR, and we conducted 2 experiments. The results show that more than 50 millimeters height curves can be detected with high accuracy. In addition, the second experiment's results shows that the curve position also can be estimated with higher accuracy. This paper is supported by the Verification Style R&D program for solving regional challenges using data cooperation and utilization by NICT Japan. Thank you for listening.